Hello, everyone. My name is Jutin Liu, and the topic of today's presentation is effect of nitrogen doping techniques on hard carbon anode materials based on sodas for sodium-ion batteries. And my supervisor is Dr. Willen Liu. Before my presentation, I want to introduce myself. I'm from Taiwan, and Joanne Christian University is my school, and it is a small but beautiful school. So if you guys have time, please visit my university. And this is my research interest. I research on anode materials on sodium-ion battery and lithium-ion battery, and I also research on cathode materials on sodium-ion battery. And this is my topic outline. I will divide this part to introduce my research. First one is introduction, and then experimental result and discussion, and the last one is conclusion. So at first, I want to introduce why I want to do this topic. Everybody knows lithium battery can apply on a lot of devices like cell phone and camera, car, and laptops. But there is a big challenge on lithium-ion battery because of lithium metal is not enough in the world. So a lot of researchers that talked about if we don't recycle the lithium metal, the lithium metal will be around in 65 years. And then we can see this picture. For picture A, the red one is lithium metal, the green one is sodium metal. So it is obvious, can see that the content of sodium metal is larger than lithium metal. And then for picture B, the cost of lithium-ion battery is lower than the cost of sodium-ion battery is lower than lithium-ion battery. And then for picture C, because of sodium-ion battery is very good to replace lithium-ion battery. So the publication in recent years is increased until 2022. And then based on the above information, so we can know sodium-ion battery, it is a lower cost material. And then because of the location of lithium and sodium in element periodic table is really close. So they have similar properties and similar electrochemical reaction. But unfortunately, sodium-ion battery is not a really perfect material because of the radius of sodium ion is larger than lithium ion. So if the despacing is not enough, or maybe the sodium ion cannot transfer smoothly and the capacity cannot be increased. So we'd better to solve this problem as soon as possible. And then for the safety issue, a lot of researchers use carbon material to be an anode material in the battery. For example, graphite, graphene, and CNT, hard carbon, and soft carbon. So there are some comparison about hard carbon and soft carbon. For the C, it means the capacity. So we can know the capacity of hard carbon is larger than soft carbon. And then you can see the E is for the economy. So we can know the cost of hard carbon is lower than soft carbon. And then for the left-hand side, because of the difference of structure of hard carbon and soft carbon. So there are different behavior. For example, hard carbon is amorphous and disordered structure. So there are two regions in the charge and discharge curve. And then for the soft carbon, because it is older structure, so it only have the slope region here. We also do a lot of paper survey, so we can know a lot of researchers do the biomass carbon for anode materials on sodium-ion battery or lithium-ion battery. For example, they use plum fruit, lotus stem, and ginkgo leaves. And then they all use the temperature effect to control the despacing to let the distance is enough to let the sodium ion transfer smoothly. And then I want to introduce this publication because it is really important. The author tells us important point. that use 600 to 2500 degrees C. And then they talked about, for example, the first one, it is a lower temperature, and the fifth is the higher temperature. The lower temperature is about 600 to 800 degrees C, and the higher temperature is about upper than 2000 degrees C. And then they all showed about it only have a absorption behavior, and then in the charge and discharge curves, it only have the slope region, and then there is no peak at 0.1 voltage in the CV analyze. So if we use the suitable temperature like 900 degrees C to 1400 degrees C, we can get the both of absorption and insertion behavior. And then we can see in the charge and discharge curves, there are two regions, is soft and plateau region here. And then the peak at 0.1 voltage in a CV curve will be exist. And then let's talk about the doping effect. Doping effect is a common modification to modify the carbon materials, and for nitrogen and boron elements, because of the location is really close to carbon, so it is easy to dope into the carbon. And then for the sulfur and the phosphorus element, because it can cause the structure deformation and alters the charge density. And someone will do maybe 2 elements or 3 elements to dope into the carbon to create a more advantage. So we also do the some paper survey, so we can know doping effect is a very common modification to modify the carbon materials. And then they also use the biomass materials. So this is here we have a short summarize. For biomass carbon, it's a porous and layer structure, and it is a non-toxic and easy to prepare, and it is a friendly environment materials. And for nitrogen doping effect, it can improve the conductivity and provide the active sites and reduce the impedance. And that goes on my experimental. I use the urea and the soda's hard carbon to be my precursor. And I use 2 methods to modify it. The first one is sintering. I use 800 degrees C and in argon atmosphere to sintering my materials. And the second one is hydrothermal method, and then I use 160 degrees C, and then samples name I code HTNHC and HPNHC, and all of the material I coded HCMS. And for the SEM images, we can see it is all shows sheet stacking like structure, and then in EDS mapping, we can know there are carbon and nitrogen and oxygen signaled here, and then the element were evenly distributed in HP and HC. We also test the HRTM images of the HCMS materials, and from the software we can know the interlayer spacing of these 3 materials were 0.342, 0.341, and 0.403 nanometer, and they are all larger than graphite 0.335 nanometer. So it means that larger deep spacing may be good for sodium ion transfer during the charge and discharge process. And the next one is XRD analyze. We use the aluminum oxide to be a standard powder, and then we can see at 23 and 43 there are 2 broad peaks, and corresponds to 100 and 002 lattice. And then after calculations, we can know HP and HC has larger lattice parameter C. We also do the Raman spectrum And then we use Gauss distribution to divide 4 parts. D1 means the graphite defect or disordered carbon, and D3 means sp3 carbon vibration, and D4 means disordered graphite lattice, and the G means the older graphite lattice. So we want to know the DG ratio. So after calculation, you can see the picture D here. And then after the doping effect, the defect ratio will be increased. And next one is XPS spectra. We can see there are carbon and oxygen signal here. And then after the doping effect, so the nitrogen signal will be exist. So for the high resolution spectra here, we can see the exist of pyrrolic nitrogen is physical to sodium ion absorption. And then because of the existence of active sites in HCMS can result in provide reversible capacity. And then we can see the BET analyze. After the doping effect, the surface area is decreased obviously, and then we can control the absorption of electrolytes through the lower specific surface area. It can integrally lower the impedance of the anode materials. And here is the table and talked about the ratio from the XPS analyze and BET analyze. So to further research the sodium ion behavior during the charge and discharge process, so we do this analyze. You can see from the charge and discharge curve, we divide 2 parts. One is sloped and the other is a plateau region. And for the slope region, it is for the absorption on defect. And then for the plateau region, it is for absorption on micropores and then intercollection between the carbon layers. And this is my electrochemical analyze. So my voltage window is from 0.1 to 3 voltage. And then from the red performance, we can know after the doping effect, the capacity is obviously increased compared to the HC bare. And then from the cycle performance, it is the capacity of the HT NHC and HP NHC is larger than HC bare, and their current peak efficiency is around 99%. And then because we test the BET, so we can know the short summary because of that's a specific surface area, so it can minimize the formation of SEI. So this impedance is lower than the other two. And then to further know the distribution about the charge and discharge process. So we use this sentence, this equation to calculate these curves. So we use peak 1, peak 2, and peak 3. We can know if the B value is close to 0.5, it means the diffusion control. And if the B value is close to 1, it's surface control. So we can know peak 1, peak 2 is diffusion control, and peak 3 is surface control. And then this is the picture to show you what is the diffusion control and capacitive behavior. Finally, we also use the HP NHC as the anode material and VP as a cathode material to prepare punch cells. And we can see it is a very stable materials, and after 200 cycles, the retention is around 86%. So in conclusion, XPS analysis indicates that the electrochemical performance was improved with a higher pyridinic nitrogen content. And then because of it have the pyridinic nitrogen can behave as a active site for electrochemical process, as this work has once again demonstrated. And then that surface area may minimize for the formation of SEI. And we can know HPN NHC, it shows the best capacity is around 351 mAh per gram at 0.1 ampere per gram. And then we also use the HPNHC to be anode materials and NIPN to be the cathode materials. And then we prepare the punch cell, and it has a good result. So I want to thanks to the NSTS and Unique Fortune Center and also MIT to give me help. And also I want to thank my professor. And thank you for your listening. If you have any questions, I will be happy to answer them.